Okay, let's look at some problems now on applying these tests. We have now 3 tests, 3 or 4 tests. So the main question is check for convergence. Now, first of all, a few general remarks. Given a series, the series either converges or diverges. Okay, so the series knows what it is doing. So it is only you who don't know what the series is doing. Okay, so there are tests. You apply these tests. Or if the series is more complicated, you throw away all these tests and you try your own techniques. And eventually you find out by convincing yourself, because convincing others is easy. You can just treat them in some authoritative way and they'll believe you. But you can't fool yourself. So you have to convince yourself that something happens to this series. You decide that it converges. Okay? And another question is, in the exam, I ask a series, check for convergence. You look at the solution key. I applied a certain test and found out that it is convergent. Then one of the common questions is, how do we know which test you are going to apply? The answer is you don't. Okay? And you don't have to. Because there is not, given a series, there is not one test which tells us whether it converges or not. Okay? So given a series, you should always consider it like this. Given a series, it either converges or diverges. Okay? And now you have lots of tools to check. You check and you try to find out. You change the terms of the series, separate it, combine it, whatever you do. You apply your own techniques and you find out what the series is doing. That's what you are supposed to do. You don't have to guess how I will do it, because you will do it in a certain way. Your friend will do it in a different way. Even in these simple cases, you see, to show that a telescoping series converges, we can either use direct comparison test or limit comparison test. Next, we will use ratio test. You will check that the ratio test doesn't work. Okay, so if a test doesn't work, then you'll try something else. But okay, you tried it. Maybe I will never try ratio test, or your friend will never try ratio test, but he tried ratio test. Okay, trying ratio test will tell us that the test doesn't know if the series converges or not. So you learn something. Okay, so then you know that the series is behaving like a p-series. So then you start comparing it with the p-series. Okay, because the ratio test fails on p-series, you take a clue from there. Okay, when we come to ratio test, we'll do this in detail. So with that in mind, check for convergence. Here I'll probably apply some tests, but other tests may also apply. So one of the things is always something like this, which looks complicated and very educated. Okay, so the first impression is that this is a very complicated series. So what test should we apply to this? Okay, it took you 5 seconds to think about series. We have only what? Nth term test, the general term. Okay, let's apply the nth term test. What does the general term do as n goes to infinity? Does it go to 0, 1, 8? What's the limit of ln n over n as n goes to infinity? Pi over 2? Apply and of that, so what do you get? No. So what is the result? Okay, you do your calculations. 0, you think. No, we don't want what you think. We want your answer. You will put your pride on it and you say, it's pi over 2. 0, 5. What?
0.
But you have to be confident. Suppose you say 0 and it is 3. What will you lose? You'll just learn that, okay, your technique was wrong. So
I did with L'Hopital.
no, I'm trying to push confidence in you. Okay, so you do something. Don't give an excuse. Your answer is 0, right?
Yeah.
Yes. Okay. That's the attitude. The answer is 0 here. So how many people think 0 is not the answer? You scared everybody. But you said yeah in such a tone that you. Okay, ln is very small. ln is computed with a polynomial. The general fact after we do lots of L'Hopital exercise, we know that polynomial always wins, and your friend did L'Hopital in his mind in 2 seconds. This goes to 0. Okay, so the general term goes to 0. What did we learn? What did we learn about this convergence of this series now? What does the general n-term test say? N-term test says that if the general term does not go to 0, the series diverges. Now we found that the n-term goes to 0. So the n-term test says this is none of my business. Okay, so we didn't learn anything, but it's always a safe thing. It's always the right thing to first check the n-term test. Okay, now n-term test says that the general term goes to 0, so we don't know what's happening. Now we are allowed. Nobody will claim, nobody will laugh at us if we try lots of other techniques. Okay, so now we try other techniques. We have integral test. Okay, it's obvious that integral test will work here because 1 over n is derivative of ln n, but we always try to do the integral test as the last resource because you have to do lots of calculations. The other thing is, okay, we have comparison test, direct comparison test, and limit comparison test. They are both almost the same thing. Okay, let's do direct comparison test. Is this smaller, the general term, smaller than a convergence series or larger? Larger than what? 1 over n. Summation 1 over n diverges, p-test. This is obviously larger. ln n is very, very small, but when n is larger than 3, it is larger than 1. Okay? ln n over n is larger than 1 over n for all large n. So in fact, if n is larger than 2, if n is 3, we start having this thing. Okay? Summation 1 over n diverges, harmonic series. So that is why we prove these things and give it a name. So now you don't have to convince anybody by giving different proofs that this diverges. This is one of the basic things that appear. So when you say summation 1 over n diverges because it's harmonic series, it's done. Okay? Now by comparison test, by direct comparison test, in fact, test summation ln n over n diverges. Okay? You can also use integral test here, okay, because ln x over x dx, this dx over x is d ln x. So you integrate this. This is ln x squared over 2. It goes to infinity as x goes to infinity. This one?
No, the whole summation.
Uh-huh.
Let's take that summation to the power e.
Huh.
And it will be what's the multiplication of n to the 1 over n?
Probably it will work, but we even avoided integral test because we will do 2 lines of calculation there. Now, if your argument, yes, it works, but you'll do lots of calculations. Maybe engineers are very active people, but we mathematicians are very lazy. We try to solve the problem in shortest possible way. So your argument will probably work because there is ln. Then if you raise it to exponential, you'll have an infinite product. Then you have to show that that infinite product diverges, which is probably true, but you will work.
Because n to the 1 over n goes to 1, n goes to infinity. So every product is bigger than 1.
Yeah, as I said, it will probably work, but the word that pops up mine is masochism. Okay, so in mathematics, we try to reserve these powerful techniques for tough problems. Okay, if the problem if the problem just is easy to see with very simple techniques, then you do that and you get rid of it. Okay, so what other common problems we have? So this one is easy. Well, and interesting. So, question is again, check for convergence. N equals 1 to infinity 1 over n factorial. Okay, our gut feeling is you should always have a gut feeling. You should always have a guess before you start doing anything. It doesn't matter whether your guess is correct or not. Okay, you make a guess. You try to prove things in that direction. While you are trying this, of course, while you are trying, you will learn new things. You will get more information. Then you can change your guess, but then you stick with your next guess. Okay? So you don't say there is a problem, there is this whole world of mathematics, all theorems, now what do I do? Okay? You get stuck. So our gut feeling is that n square, n factorial is very big. So 1 over n factorial, the general term, is going to 0 very, very fast, so it will probably converge. Okay, so the whole idea of looking at the general term is how fast the general term goes to 0. If it goes to 0 fast enough, the series converges. There are even some measures of, we will not do this in this, but if you later need techniques like this, there are different ways of checking how fast the general term goes to 0. Sometimes you have a series, none of the tests work for this, then you have to check if the general term is going to 0 fast enough. So here, nobody has any doubt in his mind that 1 over n factorial is going to 0 very, very fast. So this should converge. Okay, so that's our guess. Maybe it is wrong. Okay, so sometimes you make a very reasonable argument which sounds correct, but later it turns out to be false. It doesn't matter. Now we'll try to show that this converges. If we cannot, then we'll try to show that it diverges. Okay, so one of them should work. So since n factorial is very large in the denominator, we want to see if it converges. So integral test is out of question, okay, because the only function which is n factorial is gamma function. And here you are attempting to integrate the reciprocal of the gamma function. Okay, not even your friend will try it. Okay, so integral test is out. Okay, then we have only comparison test. Okay, we didn't learn anything other than that. We only have comparison tests now. So compare this with something you know. How many things you know? You know geometric series. This doesn't look like geometric series. You know only P series. Okay, so we have P series, we have comparison tests. These are the only things. If these things work, they will work. Otherwise, we don't know anything else. So apply comparison test with P series or something like that to this one. 1 over n square. So is this less than 1 over n square? Yes. Let's check. Okay. So your friend claims that 1 over n factorial is less than 1 over n square. When n is equal to 2, it is false. So large enough for all. So claim for all large n. So we can even check this. I think n equals 4 or 5. From there on, it will work. Okay? Or if you are not sure, prove this by induction. For induction, you see that it's probably easy to show the passing stage from n to n plus 1. It's probably easy. So let us check that if it starts at one point. Okay? So we have n squared. So we want to say, what do we want to say? We want to say that n squared is less than n factorial. So here we have n squared, here we have n, this is n, here we have n. When n is 1, this is 1, this is 1. When n is 2, this is 4, this is 2. When n is 3, this is 9, this is 6. When n is 4, this is 16, this is 24. Okay, so from here on, it will be large because you see when it is 5, this is 25, this is 120. Okay, so it will probably like this. So what we want to prove is for n larger than or equal to 4. Okay, when n is equal to 4, we are done. Okay, 16 is less than 24. Assume n squared is less than n factorial for some n larger than or equal to 4. Now we want to see n plus 1 square. Okay, so n plus 1 square is equal to what? Okay, so this is n squared plus 2n plus 1. Okay, so you do the proof. So how will I prove that this is less than? So eventually I want to check if this is less than n plus 1 factorial. Okay, n plus 1 factorial is n factorial n plus 1. Evet. I know that n squared is less than n factorial. Okay, so this is our assumption. So let's also put that here. This is less than 2n plus 1. This part is n factorial times n plus n factorial. Okay, so you see n factorial is less than this. 2n plus 1 is obviously less than n factorial when n is large. Okay, so for example, when well, here you are just multiplying this by 2 and adding 1. Here you are multiplying n by n minus 1 factorial. Okay, so this shows that you can pass from n plus 1 to from n to n plus 1. Okay, so this shows that this is true for all large n. In particular, we even know that it starts from n equals 4, but we are not interested in precisely where it starts. All we know is that all we need is from some point on, this inequality holds. Okay, now this is all positive. These are all positive. Summation 1 over n squared converges. P-test. So summation 1 over n factorial also converges. Okay. In fact, we start this from 0 with the convention that 0 factorial is 1. Okay, then this number is actually equal to e. Okay, so later we will see that this number, this sum is e. Okay, so far we only know this. So there was a calculation showing that this is less than 4. Okay, so another claim. So we found this, but we can also claim the following: 1 over n factorial is less than 1 over 2 to the n for large n. Okay, so again, prove by induction. Two to the n is less than n factorial for large n. Okay, so again, in this case, it's easier to prove. So where does it start? So 2 to the 5, for example, 2 to the 4 is 16 again. 4 factorial is 24, so it starts from there. Okay, 2 to the 3 is 8, 3 factorial is 6, so it's not working there. So n larger than or equal to 4. So it starts there. Okay, 2 to the n plus 1. Induction 2 to the n plus 1. I want to see this thing. This is 2 times 2 to the n. By induction hypothesis, this is 2 times n factorial. But 2 is less than n plus 1. Okay, n is larger than this. So n plus 1 is larger than 2. And this is less than n factorial, which is n plus 1 factorial. So this is the key step in induction. So this we proved this 2 to the n is always larger than n factorial, less than n factorial. So the reciprocal holds. Okay. So 1 over n factorial less than 1 over 2 to the n. Therefore, I know that now they converge. I can also conclude, if I didn't do this, I will also conclude from here that this converges, because this is now a geometric series, it converges, and it forces this to converge. From here, I know that 1 over n factorial, n equals from 0 to infinity, is less than summation n equals 0 to infinity, 1 over 2 to the n. I know precisely what this is. This is 1 over 1 minus 1 over 2. Is that true? And I found that this is less than 2. So this is not true. What did I do wrong here? This inequality does not hold. So let me be more precise here. So we forgot this thing. Okay. So let me do this sum. So this is true for n larger than or equal to 4. Let's continue from there. Now it will be easy. Okay, so now I want to understand this. N equals 0 to infinity. Later on, we will find out that this is equal to e, and with arguments in e, before we precisely know the value of e, we have to. Well, you will see that we will need to know that e is less than some number so that we can do some induction. Okay, so 1 over n factorial. This is equal to 1 plus 1 over 1 plus 1 over 2 plus 1 over 6 plus summation n equals 4 to infinity 1 over n factorial. Okay. So what is this side? This is This is 2 plus 1 over 2 plus 1 over 6. So 12 plus 3 plus 1 over 6. This is equal to what? 15, 16 over. I multiply this by 6, this by 3. 15, 16 over 6. Okay, let's keep it this way. So this is equal to, this is less than 16 over 6 plus summation n equals 4 to infinity 1 over 2 to the power n. Okay? So now we know a precise value. We can calculate this side, this precisely. Okay? Because here you take 1 over 2 to the power 4 out, then you have a geometric series which converges to 2. Okay? And you have this number, you add them. Let's see, well, I didn't do the calculation here, so I'll leave the calculation to you. So maybe later on I write this on the screenshots. Okay, so we know that this number is less than this number. We have a precise upper bound for this. Okay, and that upper bound in this case will probably be less than 3. Okay. Okay, so what other interesting sums we have? Let me check. Okay, so another thing. So we have things like this. So we can invent. So here I have square root something, and here, so I already wrote something, so let me invent this. 12 plus n to the 7 square root, and 31 n cubed plus 7 n squared plus 181 n plus 2017. So you know that these numbers will not be relevant in the calculation. Okay, now question is, does this converge or diverge? So this thing is amenable to limit comparison test. So when n is very, very large, okay, so you can drop this. This 12 is just a poor guy on the right-hand side. It doesn't do anything. So this denominator is behaving. So let us call this an. For n very, very, very large, an behaves like. So this is not a proof yet. We are trying. Remember, I said that you have to make a guess at the beginning. So we are trying to make a guess now. An behaves like, so this one is n to the power 7 over 2. Okay? So for our purposes, it is 3,5. Okay? So when n is very large, this part is behaving like n cubed. Okay? So this is behaving like n cubed. So this is like 1 over n 1 over 2, right? So when n is very, very large, and I have this 31, but 31 is just a number. I can take 31 out. Multiplying this by 31 or by some number doesn't change its divergence or convergence property. It will only change the sum. Here we are only trying to understand divergence or convergence. So the general term basically behaves like this. And summation of these terms converges or diverges. Die? Well, we have two choices. Make one choice, say converges, and what if you are wrong? Then we'll correct you. Okay, we have two choices. Summation of these. Do diverge. Okay. How many people say converge? How many people say diverge? Okay, by majority vote, this thing diverges. It also diverges by p-test. Okay, because p is less than 1. So it diverges. Okay, so now we make a guess. Our guess is that this thing behaves like this and it diverges. Okay, this guess, whether it is correct or wrong, it suggests that we use the limit comparison test. I take this, divide it by this, take the limit as n goes to infinity and see what happens. Okay, if it works, then we are done. If it doesn't work, then we'll check why it didn't work. We'll come back and make another guess. Okay, so let me do this and then we'll have our quiz. Tamam, 30 saniyede bunu çözeceğim. Then we will have 15.5 minutes for the quiz. Okay, so we try limit comparison test with Bn equals 1 over n 1 over 2. Okay, so we look at An over Bn. So this part doesn't change. This is 12 plus n 7 1 over 2. And here we have 31 n 3 plus 1 over 2 plus 7 n 2 plus 1 over 2 plus 181 n 1 plus 1 over 2 plus 2017 and 1 over 2. Okay, so you take the limit as n goes to infinity. You see that the limit is 31. Okay, so this goes to 31 as n goes to infinity. Okay, so you divide everything by this. Okay, then here 31 survives. These all go to 0 because their powers is less than this. Then when it goes inside, it becomes n to the power 7. Here 1 survives. This 12 over n to the 7 goes to 0. And here you have 1, here you have 31. So the limit is 31, which is a positive real number. So the limit comparison test says that whatever this does, this series does the same thing. Okay. Summation 1 over n 1 over 2 diverges, p test. So by limit comparison test, summation a n diverges.